Hi everyone, it's Mrs. V and I'm here today with Le Chatelier, and we are going to talk to you about the stresses that can be placed on an equilibrium system and what Le Chatelier is going to say about how we can undo those stresses. So let's get the whiteboard on and get started. All right, so equilibrium stresses and how to alleviate them. Le Chatelier, what does Le Chatelier have to say about that? Well, Le Chatelier says when you've got a dynamic equilibrium and you subject it to a stress, what we mean by a stress is a change in reaction conditions. And Le Chatelier says the position of equilibrium is going to move in such a way as to alleviate that stress and form a new equilibrium. So what do we mean by alleviate the stress? We just mean to try and undo the change. So whatever gets done to the system, the equilibrium is going to move to try and undo what was done. The types of stress we're going to talk about today are adding or removing reactants and products, changing the pressure, and that only applies for gases, and changing the temperature. Let's get straight onto it. Concentration changes. This is done by adding or removing reactants and products, and this can be done by injecting more gases into a system or removing reactants or products by their reaction with other substances. But the overall change we're going to look at is that we've added or removed something. So let's have a look in our table here. We've got an equilibrium system, A and B in equilibrium with C. Okay, they're all gases. And what we're going to do is add some A. So what's the stress caused by adding A? We've now got too much A in the system. So how are we going to fix having too much A? We've got to use up some A. And the reaction can easily use up some A by reacting it with B. So what we need to do is use up A to fix it. We need to use up the extra A. And the way we can do that is A and B reacting to form C. And what that means is our position of equilibrium is moving to the right. So if the position of equilibrium goes over to the right, we'll end up with less A and B and more C. And the stress then of the extra A will have been alleviated. What about if we remove A? What's the stress? The stress is now we've not got enough A. So how can we fix that? We can make some extra A. And we make extra A by C reacting to form A and B, which is the position of equilibrium moving to the left. How far across to the right or the left is it going to go? Well, the whole point is it's got that Kc, our equilibrium constant, stays the same if the temperature is the same. So the position of equilibrium is going to move across until that ratio of products over reactants comes back to the original value. So remember our Kc value, which we also call Q if it's not our reaction quotient. In this case, will be the concentration of C over the concentration of A, concentration of B. And that position of equilibrium is going to keep moving until the ratio of these concentrations goes back to exactly the same value as it was. The actual concentrations themselves won't be the same, but the ratio is going to be the same. I want you to pause the video and I want you to have a go at the next two lines of the table. I want you to work out what will happen if we add B and what will happen if we remove B. How did you go with that? So if you add some B, what's the stress? The stress is you've got too much B. How can you get rid of B? You react it with A. So we need to use up the extra B. And to use up B, that means our position of equilibrium has to go over to the right. What about if you remove B? Stress, haven't got enough B anymore. You need to make some more. And to make more B, you're going to have the position of equilibrium shifting to the left. Let's go and look at what happens if we fiddle with the other side of the equation. What about if we add C? Well, if we add C, our stress is now we've got too much C. So if we've got too much C, we need to use up C. And the way we use up C is that it reacts to form A and B, so that is the position of equilibrium moving to the left. If we take away C, our stress is now we haven't got enough C. So we need to make more. And to make more C, the reaction's got to go to the right. So you can see it's very simple to do concentration changes because you just need to think about how to either use up the extra stuff that you've put in or to make more of the stuff you put out. And that will keep going until your equilibrium constant retains its original value. All right, pressure changes for gases. Now this requires you to remember your gas laws work. So pressure changes happen by changing the volume for a gas. So if you squish the volume down to a smaller volume, squish the gas, then you get a higher pressure. And if you expand the container, stretch the gas out, then you end up with a lower pressure. Every mole of gas has got to take up the same volume if the temperature and pressure are the same. And that doesn't matter which gas it is. So if we look at our equilibrium A and B in equilibrium with C again, we can see that the left-hand side, the A and the B, that's got 2 moles of gas, whereas the C is only 1 mole of gas, which means that effectively the A and B side is taking up twice as much volume as the C side. So what we've got here is a way to alleviate pressure changes. If the volume is getting smaller, let's go down and look at our examples here. If the volume is getting smaller, so we're squishing the gas, we're pressing the container in to increase the pressure. The stress is now that we've got too many moles of gas and we've got this tiny space and it's all too crowded. How can we alleviate that stress? Well, we could go over to the side where there's less moles of gas. And in this case, in our A and B in equilibrium with C example, the side with the less moles of gas is over to the right. So in this example, that's moving to the right. If the volume gets bigger, if we stretch the container out and decrease the pressure, then the stress is now there's not enough gas to fill up all of that big room that you just made. Solution? We go and make more moles of gas. So we're going to have the position of equilibrium move to the side with more moles of gas. And in this case, in our A and B in equilibrium with C example, the side with the more moles of gas is our A and B. So in this case, in the example we're looking at, that's going to be to the left. So quick summary. If you are going to increase the pressure by decreasing the volume, the position of equilibrium is going to go to the side with less moles of gas. And if you decrease the pressure by increasing the volume, the position of equilibrium is going to move to the side with more moles of gas. There are, however, a couple of traps for young players in this one. So traps for young players are changing the volume is not the only way you can increase the pressure or decrease the pressure. You could increase the pressure of an equilibrium system by adding an inert gas. So you could actually just inject some helium into the system, and that doesn't affect the equilibrium. Think about it. Our equilibrium constant is the concentration of C over the concentration of A, concentration of B. What does concentration mean? Moles over volume. So if you injected some helium into the system, did you change the number of moles of C, A or B? No, you didn't. You still left all of that stuff in there, so you didn't change that at all. Did you change the volume? No, the volume stayed the same. You just added an inert gas. So because you didn't change the concentration here, because you didn't change the moles, they were the same. And you didn't change the volume, that was the same. You didn't change Kc, so there's no need for the position of equilibrium to move because Kc didn't change. So the system remained at equilibrium. The other one is, if there's the same number of moles of gas on both sides of the equation, then changing the volume won't change the equilibrium because you can't alleviate that stress. If you're going from 2 moles to 2 moles, you're keeping exactly the same situation. So you can't alleviate that stress if there's the same number of moles of gas on both sides. And Le Chatelier is not happy about that, but it's just something we have to accept. Let's move on to temperature changes. Temperature changes, again, we've done some work on temperature changes or energy changes in chemical reactions. And we know that there's one type of reaction that produces heat, and there's the opposite type of reaction that takes up heat, it uses up heat. Can you remember what they were called? That's right, an exothermic reaction is the one that produces heat, and an endothermic reaction is the one that uses up heat. Can you remember delta H, the enthalpy change values? The exothermic reaction had a -1, and the endothermic reaction had a positive delta H. When we're looking at equilibrium systems involving temperature changes, we're always going to be given a delta H value. But one thing you need to remember is that if it's a reversible reaction, if one way gives off heat, then the other way is going to have to take in heat. So if it's exothermic in one direction, it's going to be endothermic in the other direction. When you see the delta H value written, then it's always for the forward reaction. So here it means that the forward reaction is exothermic, and the back reaction is endothermic. Sometimes I find it easier to think about heat as a reactant or a product in the reaction when I'm dealing with temperature changes. It's not really, reactants and products are technically substances, but you know, let's just, if we've got a tool that can make it easier, let's use it. So if we've got A and B in equilibrium with C, and we know that the forward reaction is exothermic because we see this negative on the delta H, I like to think of that meaning that A and B don't only produce C, they also produce heat. And this makes it very easy for me because I'm going to think of my temperature changes as either an increase in heat or a decrease in heat. So I'm going to think of my temperature change here, my increase in temperature. I'm going to think of that as adding heat. So if I add heat, then according to Chatelier, this system is going to move over to the right to use up the extra heat. So the position of equilibrium is going to move to the, did I say right? I meant left. Position of equilibrium is going to move to the left. And that's going to use up the extra heat. If I decrease the temperature, I'm going to think of that as removing heat. So my position of equilibrium, if I remove heat, it's going to try and make more heat. So that's going to shift the position of equilibrium to the right. And that's going to make more heat to replace the lost heat. Let's have a look at a reaction that's written with, it's an endothermic forward reaction. The way I'm going to think about this one is I'm going to think of this as D and E reacting, but because it's endothermic, it's also going to use up heat. So what would happen? What would happen if I increased the temperature? Pause the video, work out what's going to happen with an increase and a decrease in temperature here. Okay, so if I increase the temperature, I'm adding heat here. So if I add heat, what's going to happen? We're going to try and use the heat up. It's going to move right. If I decrease the temperature, then I'm removing heat. I need to make more heat, so the system's got to move to the left. It makes it really easy to see that if you increase temperature, adding heat, then the position of equilibrium is going to move away from the heat and vice versa. The interesting thing about temperature changes is the value of the equilibrium constant changes. That is something we're going to discuss along with other things in our next video, but that's all I've got for you today. So I will see you in the next video.